Electrical earthing, prepared by engineer Adil Sully. We will be operating against a dark navy blue backdrop throughout this module to clearly illustrate the following technical diagrams. We begin by defining the physical mechanics of energy dissipation and how we engineer structural connections directly into the Earth. From there, we examine the specific diagnostic methodology and the field instrumentation required to test and verify these ground connections. Finally, we will analyze the strict operational compliance limits that govern acceptable electrical resistance values across different industrial sectors. Earthing is not an optional accessory. It is the foundational engineering parameter that dictates the survival and operational stability of an entire electrical network. Earthing, or grounding, is the deliberate, engineered process of connecting specific electrical components directly to the physical ground. This process targets two main areas: the external chassis of the equipment itself and specific points within the internal circuitry. The first primary objective of these connections is operational safety. By providing a dedicated, low-resistance route, we ensure that any hazardous rogue energy has an immediate path to exit the equipment, rather than discharging through surrounding materials. The second primary objective is source outcome stability. By connecting the source neutral directly to the ground, we actively stabilize the system's neutral voltage, locking it to a value very near zero. A properly engineered ground acts as the system's physical anchor. It provides both an emergency escape route for excess electrical energy and a fixed zero-point reference to ensure stable power delivery. During normal operations, isolated electrical systems accumulate passive energy hazards if they lack a continuous path to ground. Accumulated static electricity builds as a surface charge on the equipment's metallic casing. Second, internal leaked currents escape their circuit, charging the chassis from inside. An active earthing pathway captures both static buildup and leaked currents, draining them instantly into the soil. Beyond internal system faults, we must also engineer protections against macroscopic external events. A lightning bolt represents a massive, instantaneous injection of atmospheric electrical energy into a localized area. To manage this influx, the earthing system forms the essential backbone of all lightning arrestor networks, catching and routing the cloud discharge arc. Whether mitigating microscopic static friction or routing a massive atmospheric discharge, the physical Earth serves as the infinite sink required to prevent equipment destruction. Burying a conductive wire in the dirt does not guarantee a functional safety pathway. The actual electrical resistance of the surrounding soil environment must be precisely measured and quantified. To verify this, engineers utilize a specific diagnostic instrument known as an earth tester or earth meter. The earth tester uses test probes driven into the ground at points H, S, and E, separated by exact 5 to 10 meter gaps. Current injected through the red and yellow lines meets Earth's resistance, producing a measurable voltage drop registered on the device. By executing this test, the meter effectively incorporates the raw ground into a temporary circuit, allowing us to quantify its hidden conductive properties. The internal schematic reveals how the earth tester processes data. Powered by an AC or DC supply, an ammeter tracks current across the outer loop from electrode 1 to 2. Simultaneously, a voltmeter connects to movable electrode 3, measuring the soil's potential difference. The device then calculates the final value using Ohm's law. Resistance equals voltage divided by current. This direct mathematical relationship forms the basis of electrical safety verification, converting raw voltage and current readings into actionable proof of compliance. The acceptable resistance for an earthing pathway is not a single universal number. It is strictly dictated by the scale and function of the facility. This chart details the required limits. For standard residential structures, the earthing resistance must be maintained at or below 5 ohms. However, as an operation's reliance on continuous uptime and data integrity scales up, the tolerance for electrical resistance scales down. Industrial complexes, telecommunication hubs, and data centers process massive amounts of sensitive information. They require a much stricter grounding threshold of less than 1 ohm. Moving to the top tier of infrastructure, systems carrying massive electrical loads require the most frictionless path to ground mathematically possible. utility-scale power transmission demands extreme tolerances. Medium voltage networks are restricted to 0.5 ohms, while high-voltage systems must achieve an earthing resistance of 0.3 ohms or less. We see a direct inverse relationship. As the potential energy of a system increases, the required resistance of its safety pathway must drop closer to absolute zero. An earthing system is an active, heavily engineered mechanism that requires exact physical measurement. Meeting these precise resistance thresholds ensures the safe routing of rogue currents and guarantees the baseline power quality of the network. Without a verified low-resistance connection to the Earth, the isolation of circuits fails and the stability of the entire power grid degrades. Validating this grounding pathway through rigorous field testing remains a critical discipline in the application of fundamental electricity.